Okay, I thought I'd just reach out and say hi to everybody. So since a lot of times you watch me on recordings, I did those recordings a little while ago. So, I may look a little older and wiser at this point, but the reality is the math doesn't change. And so what I want to do is go through some examples similar to what I did in the videos. So a lot of students are kind of struggling when it comes down to the last three questions on your packet that's due tonight. So really videos that I have in course content numbers 49 through 54 really kind of break down those last three questions and how you do it. But just in case anybody happens to hop on while I'm doing this, you could join in the fun. If not, it's going to be in the Blackboard Collaborate Ultra recordings so that you can see yet a different example and have me talk through that and share my screen and hopefully be able to use all the technology of Blackboard Collaborate Ultra for that. So without further ado, now that I guess those of you that are watching this got to see me, I'm going to go ahead and just go to the whiteboard. So technology is certainly different, but I'm continuing to build videos and things like Calc 1, Calc 2, Calc 3. And so I really like kind of being able to stand up at a whiteboard versus sitting down at a computer and that type of stuff too. But anyway, so I'm going to switch over here. Have you, I got to go into tablet mode here. I'm sharing the whiteboard here. So hopefully this works out. What we're going to do, I'm just going to start out basically looking at an example of standard deviation. So that's what we're gonna look at, standard deviation. And looking at standard deviation, so I gave a test in my Calc 3 class, and let's say that the test scores were given by the following. Whoops, I didn't want. I'm going to put them in smallest to largest. That's kind of the easiest way for me to keep track of it. So one student got a 71, another got an 82, another got an 85, another student got an 88, and then the best score was a 94. So, if there's only 5 students taking that advanced course, what would the standard deviation be? Well, the first thing I got to do is figure out what the average score is. And there's multiple different types of averages. There's a median, which is a middle number average. Of course, that's 85. So the median is 85, but that's not the average I'm looking for. When we look at the median is used in the 5-number summary, which is actually videos that I had earlier. But for the standard deviation, we want to use kind of the average that you usually have, and that's X bar, or you add them up and divide by the total number. So this is going to be the sum of the X's divided by the number of people that took the test. Well, if I add all these numbers up, I'll let you verify this, but when I add all those numbers up, I get 420. And divide that by 5. I'm just going to do this in my head because I don't know what 420 divided by 5 is without some math. Some of you might say, well, 5 goes into 42 8 times and then to 24 times, but I'll tell you how I do this. I'm going to take 420 divided by 10, which is really easy. That's 42 because all you do is move the decimal. And since I'm only dividing by 5, which is half of 10, I double that answer and get 84. So my average score is 84 for these. And then to find the standard deviation, which is based on the mean average, so this is the mean, to find the standard deviation, what I'm going to do is I'm going to look at the observation, the test score, individual test scores minus the mean. So I'm going to see how far away that is. And then I'm going to take that number. Sometimes that's going to be negative and sometimes it's going to be positive. So then I'm going to take that observation, which we could just call those X's, minus the mean squared. I'm going to square those up, and then once I do that, I'm going to add all those up, but then I'm going to divide by the total number of students that took it, and that's going to equal the variance, which is the square of the standard deviation. So if I call the standard deviation little s, sometimes it's called sigma when it's really idealized, but this would be s squared. So then I just got to take the square root. So I'm going to do that. I wrote these numbers down. So I've got a small whiteboard here, unlike when I have my screens up. So I'm just going to call my observations my x sub I. So x sub 1, x sub 2, all the way through x sub 5. So I got 5 students, you know, Jimmy, Sally, Johnny, Freddie, and Elvis. Okay, but anyway, those are the, so what is x sub 1? X sub 1 is the first score. That's the first student's test score is 71, and then I'm going to subtract the average test score and I get minus 13. Well, what does that mean? That means that this first student, I think that was Jimmy I said, but anyway, Jimmy scored 13 lower than the average score. So that's what that minus represents. And we can do this for, so x1 is 71, x2, the second score was 82. Well, I don't know if this was Susie or who, or Sally, can't really remember my students' names, unfortunately, when they're made up. But this student had a score that was 2 below the average. And then the third student had a score of 85. Well, if you notice, when I subtract the mean of 84, we get a positive 1. Well, what does that mean? That means that Johnny, I think this one, was scored 1 higher than the mean. So I just wanted to double check that I actually started the recording. I'd hate to do all this all over again. But anyway, so he was above the mean, above the average. He had a score that was above average. And then the last 2 students had 88. That student scored 4 above the average. And the last student had a score of 94. And of course, subtract the mean of 84. And we'll get that this last student actually scored, had a score that was 10 above the average score. And so then, since we, by the way, I just want you to notice something. If I add up all these numbers, we get minus 13, minus 2 is minus 15, and then plus 1 plus 4 plus 10 is plus 15. So the sum of this is 0. Well, it should always be 0 or about 0, depending on if I had to round my mean off. And so that's not very exciting. So this is why what we do with all these numbers is we square them up. So we take the observation minus the mean and we square each one. And doing that, minus 13 quantity squared is 169. 2 squared is 4. 1 squared is 1. 4 squared is 16. 10 squared is 100. And then what I want to do is add all these up. So I'm going to add up, by the way, this is the deviation from the mean. That means how far away from the mean. So that's the deviation from the mean. And if you notice, some of those observations lie below the mean or to the left of it, and some of the test scores or the observations lie above the mean. So this is the deviation from the mean. And what we want to do is we want to square it up so that we don't add up to 0, because that really doesn't talk anything about the standard deviation, which is a measure of spread. So if I add all these numbers up, I'm going to end up getting 290. And then what I want to do is I kind of want to take the average of the squared deviations. And so to find that average, I'm just, in your book, we're using the simple version of standard deviation. There's 2 different types. So I'm going to divide that by 5. In some books, or the standard deviation, if let's say we didn't know this one, but I knew the other 4, if I know that it adds up to 0, I could use algebra to figure this one out. So every once in a while, instead of dividing by n, they might actually divide by n minus 1. So this is n minus 1. That's called the degrees of freedom. So for a normal, for a regular standard deviation, you know, when I teach statistics, we would divide this sum of squared deviations by 4, not 5. But in your book, and the simple version of standard deviation, we're just going to divide by n, not n minus 1 degrees of freedom. By doing that, once again, dividing by 5, I'm going to divide by 10, I get 29, and then I double it and I get 58. Now, you might think, well, 58, that's a nice, nice number, but that's not the standard deviation. That is, remember, we squared everything up here and took that average and got 58. So what we want to do, this is actually going to be the square of the standard deviation. So the standard deviation then is going to be the square root of 58, or in this case, about 7.6 to the nearest tenth. Okay, now the standard deviation is a measure of spread. So the answer for this standard deviation is 7.6. If we're going to 2 decimal places, it's 7.61. Okay, so once again, standard deviation measures spread. A lot of times if we have a normal curve, which we have other examples that talk about that, we're going to use the mean, which is 84, and that's a measure of center. 84 is a measure of center or middle, and standard deviation is a measure of spread. So we're going to look at some data that's very nicely distributed. So let's say that that test was based on, if we have on a test that lots of students besides my 5 took, and let's say that overall the distribution of test scores is so nicely distributed that it ends up looking like a normal curve. So this is a normal curve, which we look at the normal curve with the mean and the standard deviation is what it's based on. So a lot of times they'll call that N of, instead of X bar and S, that's kind of like for limited data, like if there's 5 students or 100 students, things like that. But if it's idealized, sometimes they write the mean as mu and the standard deviation as sigma. But long story short, the mean we can either represent with X bar for a specific number of people, or if it's for an entire population, we call it mu. And then standard deviation, call it S or S sub X, since X is our variable, for a specific number of data. But if it's for the entire population, they use sigma instead of S. So a lot of times you're going to say N of mu sigma, but what happens is a lot of real data is very nicely distributed, where a lot more of it's in the middle, and then it's harder to be out to the right and out to the left, where this is the x-axis right here. So this x-axis is actually an axis of test scores. So if you notice, a duh factor, x can't be more than 100 without extra credit, and it can't be less than 0. But where does my bell curve or normal curve look like? The mean is in the middle. And what happens is we know that left of middle, half of all students of the entire population of all students that have ever taken this test, let's say that's 100,000 students, half of them would have scored less than 84 and half of them would have scored more than 84. Okay, so that kind of splits the curve. And then it's kind of like area under a roof. If I'm in the attic, and when I was a kid, I had to sleep in the attic. Not really true, because I would get my parents in trouble. But anyway, you wanted the middle of the room because you had more headroom, right? So similarly, there's more area here. And then the question is, how does the standard deviation come into play? Well, what I'm going to do is I'm going to go 1 standard deviation away. I'm going to use red. So 1 standard deviation away, in this case, we said, I didn't say let's say that all 100,000 had a mean of 84 and a standard deviation of 3. So they weren't, let's say that normally, students aren't as spread out. So instead of the 7.6 or 7.61 I want to make my life easy on trying to explain this to you. And of course, if I add 7.6 too many times, I get above 100%. So anyway, so basically 1 standard deviation away from the mean, above or below, I'd add 3 to get up there, I'd subtract 3 to get here. And basically that's 1 standard deviation away from the middle would be scores between 84 and 87. Now, it doesn't matter if you say on or in between, because if I include that score, it doesn't change the area. But the roof is like area under the roof. 68% of all students, and we said like 100,000 students, but the entire population of test takers would have got a score between or on or in between 84 and 87. So this is an approximate rule. That rule is called the 68, 95, 90. Whoops, I don't want 95 in red. Sorry. I'm going to erase that. look at that. I even can erase with this software. It's awesome. Go back, get my color blue. 68, 95% would be within 2 standard deviations away. So 3 more to the left or 3 more to the right for a score. So basically 81 to 90, what do I know? I know that approximately 95% of all of the test takers would have a score between 81 and 90. So we got 68, 95, and then in most books it's 99.7, but in your book they actually call it 99.8. So they have a 68, 95, 99.8 rule. And this is an approximation, and it's based on the number of standard deviations away from the middle. But the reality is, so if I go 1 more standard deviation above and below, and that would be subtracting 3, which is the standard deviation, I get 78, and adding 3, I'd get 93. What we can say then is approximately in between these lines, approximately 99.8% of all test takers, which is 998 out of every 1,000 would have scores between 78 and 93. And of course, if there was 100,000, that means 99,800 would have had scores in between here, which means only 200 students out of the 100,000 would have had a score bigger than 93 or lower than 78. So in other words, in this scenario, this example, if the population had an average test score of 84 and a spread or standard deviation of 3, that would be the case. Okay, now these are just made up numbers, but this is real life data that we can use based on a huge population. What's a huge population? I gave an example in your other videos that you have in course content of ACT scores. So we have hundreds and hundreds and millions of students that have taken the ACT score. So we have a huge population of data that typically standardized test scores, heights of men, weights of babies, they're all normally distributed like this. So let's, so this is the picture. You might want to take a picture of this because I'm not going to be able to keep it, but we have certain questions that we may want to answer. So I'm going to go ahead and erase that because I have it, wait a minute, I have it written down. Let's see, 84. Oh my goodness. You guys let me mess up because nobody's on the video right now because I didn't give you much of a chance. I went from 84 to 84. I'm pretty sure I don't know how to subtract 3. And so these numbers are wrong somehow, but because I'm not good at math. Anyway, not a big deal. It's only recorded, and as long as you're in this class this semester, you'll be able to prove that I screwed something up. Anyway, subtracting 3, I get 81. So if that confused you, it should have. And I just needed 1 student to jump on right away, and then or look at my work that I did on my scratch paper beforehand, and I would have seen, okay, so that makes more sense. So 200 people either scored above 93 or below 75, which really, since it's symmetric, about 100 people out of 100,000 would have scored higher than a 93, and about 100 people out of 100,000 would have scored less than a 75. Wouldn't you like those chances on trying to get 75 or above, like on your midterm or final, which obviously those questions and time limits are a lot tougher, and that's why I have all these other points available for you to help you out. But anyway, so we have this. So this is actually what I have for my picture. So you might want to take a picture of this quick, and then I'm going to ask you some questions on here. So let me clear this and then answer some questions. So some of the questions are, first of all, what are the chances, what's the probability, so I'm just going to put P, what's the probability or chances that a randomly selected test taker would actually score less than or equal to 87 for their test score? Well, if I just real quick draw my graph over here, sorry, what was in the middle? In the middle was 84, right? And so that, I believe, I think I used red, blue, green, not real sure, but I didn't take a picture. Anyway, but this is 87 right here. Well, if you remember, so less than or equal to 87, well, what I do know is from here to here, that's 68, right? Which means, and of course, from the middle line over, that's 50%. I know that half of everybody scores less than the mean of 84. So the question would be, how much is in this part? Well, that'd be half of 68, right? Which would actually be 34%. So the probability that I'm less than 87 or less than or equal to 87 would be 50 plus 34% or 84%. So 84% of all the test takers would have a score less than or equal to 87. Once again, it doesn't really matter if I include or don't include the point of 87 because that doesn't change my answer. So this is using the estimate of the 68, 95, 99, 8 rule. Anytime we can use that rule, we want to use it. All right, so hopefully that makes sense. And then I'm going to clear that off. Let's go back and draw something. And what next question is going to be, what is the chances or the probability that my score, that an individually selected test taker scores more than 90 on their test? Well, in this case, I'm just gonna draw this up again. So scoring more than 90, that's a horrible picture, by the way. Anyway, but scoring more than 90, or that's a little bit better. What would that look like? So first of all, right down the middle is 84, and then we had, I believe it was red. So I'm just going to put the red in there was 87. That's one standard deviation away. And then the next one, I think I used blue for you guys, but can't really remember. Anyway, I'm going to use blue this time. So there's the 90. And really, and then I had one more, which I thought was green, and that was 93. And so the question is, hey, what's the chances that I score more than 90? Well, since that's 1, 2, or 3 standard deviations away, first of all, I know that this side over here, this half, is 50%, right? And then I also know that from blue to blue, so in this case, that was where I messed up, so I better step this out. 1 standard deviation to the left was 81, 2 standard deviations to the left was 78, but from 78 all the way to 90, so that's the second part of my rule, 95% of all people would have test scores there. So the reality is what's from 84 to 90 would be half of that. So if I cut that in half, that would be 47.5%. Now I know in your videos, or I mean the lab packet, it talks about 47.7, and the reality is that's because that's using the table that I'm going to talk about here shortly. But my personal rule is that anytime I can use the 68, 95, 99, 8 rule, I want to use it. So by the way, this 47.5 and 50 is what I don't want, which is left of this. So that's 97.5%. Score less than or equal to 90. So what's my answer over here? Would be 100% to be everybody minus the 97.5% that I don't want, which is actually 2.5%. So that's one way to do it. So 2.5% using the 68, 95, 997 rule. Let me just revisit that one quickly and say, because there are other ways to do it. In fact, maybe I explained it just slightly different in my video anyway. But if I'm drawing my curve, and then here's my 90, which we had in blue, and I want this for my answer. But the reality is the other blue one, 2 standard deviations away, was 84 minus 6, so 78, right? But what I do know is that the middle here is 95%. That's the middle. And then if I just eliminate the middle, I'm left with the 2 blue shaded tails. So the 2 tails would have how much? They'd have 100% is all of it minus the 95 in the middle would be 5% for the two tails. So if I have two tails, but I only want one of them, I just divide that by two tails. And I might have mentioned divided by two tails, Charles Dickens' Tale of Two Cities. Anyway, that's another way that we can use that 68, 95, 997 rule to get 2.5% of all students would score above a 90. Okay, so then let's just do one more where I'm using that rule. And then I'll show you when you can't use that rule, what you do, and that's when we got to use the table. And I think that's one thing that's kind of messing with students. But anyway, we'll get it figured out. So now let's look at, hey, what are the chances that a randomly selected student, student X, scores between 90 and 87, or between 87 and 90? Okay, so I want to know, hey, I randomly selected student X. What's the chances that their score is between 87 and 90, or on and in between? Okay, so let's just draw this out. Well, first of all, we knew that 90 was in blue, right? That was 2 standard deviations away. And then, of course, in the middle, we have 84, right? And then we also know that red, I think, is what we had for 87. So 87 was in red, 1 standard deviation away. 90 is 2 standard deviations away. And the answer to my problem that I want is right here. So red and blue make purple, right? So I'm just going to use purple. So I want the probability or the chances that my score is in here. Well, the nice thing is there's a couple different ways to do this, but one thing I could do is I know that, hey, from red to red is 68%, right? Which means that, well, that's right. So that would be here, right? That would be all of that. And of course, over here, that's down, if I can subtract correctly this time, that's 81. But then I also have the blue, 2 standard deviations away, would be 90, and then this one was 78, right? Subtracting another 3. Well, what's the blue do? The blue is all of this all the way over, right? So the entire from 78 all the way to 90 is 95% with my estimate. And what is the purple that I want? Well, I want this right here. But notice that that area is exactly symmetric to this area. So if I said, hey, what's the purple for both sides? The purple area for both sides would be the 95 minus 68. So 95 minus 68 would be 27% would be in these 2 purple areas. Of course, I only want the one on the right. So what I'm going to do is I'm going to divide that by 2 equal parts, and I'll get that 13.5% is the area or the chances that somebody scored between 87 and 90. Okay, so hopefully that makes sense, and that's using the 68, 95, 99, 7 rule and the symmetries for the area I want. So long story short, if you land 1, 2, or 3 standard deviations away, which is a 93 on either side, and over here it was 75. I think I was using green for those. Anyway, 93 and 75. If you're 1, 2, or 3 standard deviations away, use a 68, 95, 99, 8 rule. Okay, so now let's clear that off, and let me come back and do another example, maybe 2. Let's see how much time we have. But of course, you have my videos, right? So now what I want to do is I want to say, hey, what's the probability or the chances that a randomly selected student would score more than 85? So let's just draw that out. So I want that. So I'm gonna draw it down here, and I know right in the middle is 84, right? So 84, but then 1 standard deviation away was 87. Well, that's not what I want. Let's use orange for what I really want. So there's 85 right here. So 85 is in orange, and I want the probability that I score above that. So I want the probability that I score to the right of that. So long story short, I cannot use the 68, 95, 99.8 rule because I am not 1, 2, or 3 standard deviations away with a score of 85. So what we do is we standardize these tables, and then what I really want to do then is make this look like, I want every normal curve to look the same. And so instead of an x-axis over here, I have what's called a z-axis, where z is the standard normal curve axis. And so the mean or the middle, no matter what it is, whether it's a score or a baby's weight or a man's height, is going to be 0. And the standard deviation away is 1. So in this case, that 87 that I have over here now looks like a 1. And then this would look like a -1 instead of a, over here, what was it? It was 81 when we did our math correctly, right? So that's -1. So this, the z-axis just tells you how many standard deviations above or below the mean. So this is the number of standard deviations. If it's positive, it'd be to the right of the mean. And if z is negative, it lies to the left of the mean. So if I keep with my color code that I think I had on the last one, I used 2 standard deviations above or below was in blue, and green was 3 standard deviations above or below, so that'd be -3. So a z-score of -3 would have been the same as, I believe this was 75, right? And we had a blue one over here of 78. So 78 is 2 standard deviations below the mean, so that'd be a -2 over here. So anyway, the question is, how do we change that over then to a z-score? So this is the probability that z is greater than what? We need to figure out some number. Well, if I draw this symmetrically, it's some number in here, right? This is the z-score that I'm looking for, the specific z-score. I put a line in my z's, by the way. So I'm looking for this area right here. Well, to find a z-score, we have a formula. So the z-score or standardized score is the observation, which is your x value, minus the mean, which is x bar, divided by the standard deviation, which is s. Okay, so instead of x bar, we were idealizing it. So let me erase that. Instead of x bar, whoa, what is that? I'm pretty sure I did not mean to do that. I meant to hit eraser. It's going to let me erase. It did. All right. So anyway, instead of x bar, we were saying, and I got to make sure I still have orange. The mean we were saying was mu, and then the standard deviation was sigma. But long story short, observation minus the mean divided by the standard deviation. So if you just say the words, that's fine. So the observation that I'm looking for in this case is 85. Minus the mean, of course, what was this normal curve over here? This normal curve was n of 84, 3. So this is 85 minus 84 divided by the standard deviation, which is 3. So this is mu right here, and this is sigma, 84 and 3. All right, so we've got this, which is 1/3. Of course, we want to make that into a decimal and go 2 decimal places because that's what our table that you have is. So the z-score is 0.33, which looks like that makes sense. So this orange z-score is 0.33. So I'm really looking for the probability that z is greater than 0.33. Well, if we look at our table, now I'm going to try and share an application or a screen, I hope. And let me see. I don't know if this is, nope, that's not the one I want. Share application. I want the other one. So I got to stop sharing that. I wanted to share this one, I think. Yep, right here. So hopefully you're able to see this z-score, which I can't, you can just see my shadow of my pen here, but there's z. And what this table gives you is the area between the middle, which is, it has a 0 for the number of standard deviations away on the standard normal curve. So that's like where my 84 was when I had the actual numbers there, and the z-score. So the table gives you the area or probability in between. So it's really the area in between out of 1. So I want a z-score of 0.33. So here's how you read the z-score. You go down for the tenths and you go over for the hundredths. So I got to go down to 0.3, which is right here, into this row, and then I go over into this column to get the 3 on the end. So 0.33 is the z-score, which goes down and over. So 0.33 line up and give us 0.1293, which is the area in here. So let me go back to my picture, hopefully, and we're going to remember 12.93. So I can stop sharing, go back to my whiteboard. I'm really hopeful that my picture is still there. Hey, it is. So what did the table show me? So I'm gonna change my color here. I'm going to use purple for what it actually showed me. So the table was showing me this area. So the area there in purple is 0.1293. Now that's out of 1. Or we could also say that's 12.93% of all test takers had a z-score between 0 and 0.33. So what do I need to do? I need to take the entire half, which is 50% over here, and I need to subtract that away. And that's going to give me the orange. So the orange area is going to be to the right here, and whether it's to the right there or to the right of 33 here, I'm going to draw it over here, is going to be the 50%, which is the entire side minus the purple is what the 12.93%, and that's going to give us, 50% is the entire side. I'm going to call that black. The entire side, is black. 50% minus the 12.93% will give me the orange part, which is right here, or better yet, on the right side here. That orange part is a better picture. But anyway, 50 minus 12 is 38. So it's about 37.07%. So the answer to that using your table is 37.07% of the people score higher than a z-score of 0.33, or better yet, score higher than 85 on the test. So hopefully this additional example with me explaining it through again and having you see me right as we go is helpful for you to finish up and do the lab packet. And I will say this, I do expect every portion to be answered. If I get a bunch of answers that are wrong on this, I'm going to send it back to you, ask you to redo it. And if you completely throw your hands in the air and say, there's no way I can do that, I can't get it figured out, things of that nature, and you just want to lose the points, then I will take off points for those and then send you my key. But I'm hopeful that between videos number 49 through 54 on the standard deviations and normal curves and standard normal curves and z-scores and using the table is going to help you along with today's recorded session, which will be in Blackboard under Blackboard Collaborate Ultra under recordings. All right, thanks a lot. Reach out with additional